Imagine you get like a minor cut on your arm, right? So your body does what it's supposed to do.
Right, it calls in the cellular paramedics.
Exactly. The immune system arrives to heal the wound. But instead of patching you up and leaving, these paramedics decide to barricade the doors, dismantle the walls of your house, and then just slowly set the entire structure on fire.
I mean, it sounds like the premise for a horror film.
It really does. But that terrifying kind of paradoxical scenario is exactly what your immune system is doing in a surprisingly common yet really rarely talked about condition.
Yeah, it's a brutal reality for a lot of people.
Welcome to the Deep Dive. We know you, the listener, love getting straight to the core of complex topics without, feeling overwhelmed by a mountain of data, so we've done the heavy lifting for you today.
We definitely have.
Yeah, today we are looking at a stack of dermatological guidelines, clinical reviews, and cutting-edge research papers, all centering on a condition called lichen sclerosus, or LS.
And our mission today is to answer a really highly specific, fascinating question.
Right. Does oxidative stress actually drive the severe tissue damage seen in this condition?
It is a phenomenal question because it challenges how we traditionally view skin diseases.
Yeah.
To set the stage for you, lichen sclerosus is a chronic, deeply underdiagnosed inflammatory disorder. It predominantly affects the mucocutaneous tissue of the anogenital areas.
Okay.
And the clinical data reveals a really unique demographic pattern here, what we call a bimodal peak.
Let's unpack that term for a second. Bimodal peak, meaning it hits two very distinct separate age groups the hardest.
That's it. It primarily shows up in prepubertal children, often around the age of 7 or 8.
Wow, that young.
Yeah, and then we see a second massive spike in postmenopausal women. Think about the massive difference in those life stages.
It's totally different.
Exactly. For a young child, dealing with severe genital discomfort is terrifying and, often misdiagnosed as something else entirely.
And then for a postmenopausal woman, I imagine it's frequently dismissed as just a normal part of aging or, hormonal changes.
Right, exactly. And we should definitely add that it certainly affects men as well.
Yeah, in men, it's actually one of the most common causes of acquired phimosis.
Which is incredibly painful.
Right, it's a severe, often painful tightening of the foreskin. But across the board, regardless of age or gender, the symptoms are incredibly intense.
They are. We are talking about severe itching, debilitating pain, and the formation of these distinct ivory-white atrophic patches of skin.
Basically, the tissue thins out, and eventually it can scar so severely that the anatomical structures literally fuse together.
It completely eradicates the normal architecture of the tissue.
Which brings us to the core of our deep dive today. Researchers are realizing that LS isn't just like simple inflammation.
No, not at all.
It is a fundamental breakdown of tissue homeostasis. The body's ability to maintain and repair itself completely collapses.
And the data overwhelmingly points to oxidative stress acting as the wrecking ball here.
Yeah, the microenvironment of the skin just undergoes this radical physical transformation.
So to really grasp how the tissue gets dismantled in LS, we first have to understand what oxidative stress actually is on a cellular level.
Right, and what triggers it in the first place? I was trying to visualize this, and the best analogy I could come up with is to imagine leaving a beautiful, classic vintage bicycle out in the rain.
Oh, I like that.
Yeah, so the chronic inflammation happening in the body is the rain. The reactive oxygen species, which, drive oxidative stress, are the rust.
Right, the rust.
And that rust starts silently eating away at the structural integrity of the bike, which, in the human body, that metal frame is the collagen and elastin in your skin.
That analogy perfectly captures the slow, kind of insidious nature of the damage. Let's look at the initial trigger, the rain in your scenario.
Okay.
The pathology of LS involves a very specific immune response. It is a Th1 dominant profile.
Meaning the T helper 1 cells are the ones leading the charge.
Right, they are the generals directing the battle. These overactive immune cells just flood the local tissue with pro-inflammatory cytokines.
Particularly one called interferon gamma, right?
Exactly. Now, launching a localized inflammatory storm like that demands a massive amount of cellular energy. The cells are working overtime.
And as a metabolic byproduct of all that energy production, they generate high levels of reactive oxygen species, or ROS.
A rust.
To rust.
Yeah, normal human bodies handle a little bit of rust every single day. We have cellular mechanisms built specifically to neutralize reactive oxygen species.
But in lichen sclerosus, the amount of ROS generated by this Th1 immune response is staggering.
The balance between tissue injury and regeneration is completely shattered. I mean, the tissue is quite literally overwhelmed.
Wait, I want to push back on this fundamental concept for a
For
second.
sure.
Inflammation is like an evolutionary mechanism designed to heal and protect us, like the paramedics I mentioned earlier.
Right.
Why on earth is an immune response suddenly generating these toxic free radicals that destroy our own healthy cells?
You're touching on the tragic irony of autoimmune and chronic inflammatory conditions. You are entirely correct that inflammation is meant to be a transient healing response.
Yeah, they come in, fix it, and leave.
Exactly. The paramedics arrive, neutralize the threat, fix the problem, and get out. But in LS, the response is prolonged and completely uncontrolled.
So they just stay there.
Right. The regulatory signals that say, okay, the job is done, shut it down, they're missing. So the paramedics never leave.
And in their hyper-vigilant state, they start tearing down the building.
Exactly. When we look at the cellular level, we can see exactly what these reactive oxygen species are destroying, and it perfectly explains those painful white scarring batches.
Let's get into that cellular carnage then. What exactly is this rust eating away first?
Well, the first major casualty is lipid peroxidation.
Okay, lipids. We are talking about fats.
Right. The vital fats that literally make up the cell membranes. Think about the basal cell layers of the epidermis, the very foundation of the outer skin.
Every cell is encased in a protective lipid bilayer.
Yes, and when reactive oxygen species attack these lipids, they steal electrons, completely destabilizing the entire structure.
Hang on. If the membrane is made of fat, and that fat gets oxidized or rusted out, does the cell just burst?
It compromises the membrane to the point where the cell literally ruptures and dies.
Oh, wow.
Yeah, and this mass cell death in the epidermis leads directly to the severe thinning or atrophy of the skin that patients experience.
That makes so much sense. The skin becomes incredibly fragile, like wet tissue paper, right?
Yeah, exactly.
Because the actual fat membranes holding the outermost cells together are being oxidized and destroyed.
But the destruction doesn't stop at the surface level fats. As we move deeper into the dermis, we see profound protein oxidation.
Okay, so the structural proteins, the collagen and elastin that gives skin its strength and bounce, those are severely damaged too.
Right. When these proteins oxidize, they cross-link abnormally. They lose their elasticity and their normal three-dimensional structure.
So the rust is destroying the fat membranes, causing the skin to thin out on top, and it's simultaneously destroying the proteins underneath.
Exactly. So that flexible support structure turns into hard, inflexible scar tissue.
That cross-linked oxidized collagen directly correlates with the dense white dermal sclerosus, the intense scarring that replaces healthy tissue.
But this raises a glaring question, right? Why isn't the body fighting back?
Yeah, we mentioned earlier that bodies normally have mechanisms to handle rust.
Right. Well, clinical analyses of LS tissues reveal something deeply concerning. These tissues have abnormally low concentrations of critical antioxidant enzymes.
So the cleanup crew is missing.
Entirely absent or severely depleted. Specifically, enzymes like superoxide dismutase and manganese superoxide dismutase.
Okay.
You can think of these enzymes like a microscopic hazardous materials team. When a free radical sparks, this team swoops in, neutralizes the volatile molecule, and turns it into harmless water and oxygen.
But in LS, that hazmat team is effectively gone.
Right, allowing the oxidative damage to run completely unchecked.
Man, so you have this massive, unyielding storm of inflammation generating an endless supply of rust. And the body's natural anti-rust treatment is nowhere to be found.
It is a brutal combination.
Yeah.
It creates a compounding nightmare for the local environment. Because the tissue damage doesn't just sit there passively. It triggers a chain reaction that essentially chokes the skin to death.
Wait, how does it choke the skin?
Well, as those structural proteins oxidize and form that dense fibrotic scar tissue you mentioned, they physically compress the local capillary beds.
Oh, vascular sclerosis. The scarring gets so dense and heavy that it physically strangles the blood vessels supplying the area.
Exactly. And when you restrict blood flow, you restrict oxygen and nutrients. This creates what is known as ischemic stress.
Wow, so the cells in this area are now facing a two-front war.
They really are.
They're being battered by toxic free radicals, and at the same time, they're suffocating from a lack of oxygen.
And here's where the biological cascade gets really fascinating, because all this damage actually tricks the immune system into attacking even harder.
Through a concept called epitope spreading, right?
Yeah, exactly.
Let me see if I can map this out for you, the listener. You have your normal, healthy skin proteins, right? But the massive oxidative stress, the rust, literally bends and alters the physical shape of these proteins.
Yeah, it creates brand new, unfamiliar structures.
I picture it like the oxidative stress takes a normal, friendly protein and slaps a fake mustache and dark glasses on it.
That's hilarious, but accurate.
Right. So the immune system comes patrolling by, looks at this altered protein, and says, wait a minute, I don't recognize you. You must be an invading pathogen.
And so it starts generating autoantibodies specifically designed to attack it.
That is just a brilliant way to visualize epitope spreading. The immune system is essentially being deceived by the damage it caused itself.
Researchers have specifically highlighted autoantibodies against extracellular matrix protein 1, or ECM1, and basement membrane zone proteins like BP180 in LS patients.
So the body is generating a brand new autoimmune allergic reaction to its own damaged debris.
It really is. The initial inflammation causes the oxidative damage. The oxidative damage physically changes the shape of the skin's proteins.
And then the immune system sees the new shapes, assumes they are hostile invaders, and launches a second wave of inflammation to attack them.
Which, of course, generates even more reactive oxygen species, more damage, and more altered proteins. It is a vicious, self-perpetuating loop of friendly fire.
That's wild.
And for you listening, if you've ever wondered why chronic autoimmune conditions like LS are so notoriously stubborn and difficult to treat, well, this is why.
Yeah, you aren't just fighting a single isolated trigger.
No, you are fighting a cascading loop where the body's desperate attempt to clear the damage actively creates more of it.
That paints a really vivid, somewhat bleak picture of the battlefield.
Yeah.
But what does this all mean for the long-term health of the tissue?
Well, we've seen how oxidative stress destroys the lipids on the surface, the proteins in the dermis, and chokes off the blood flow.
Right.
But the research points to something far more dangerous happening deep inside the cells themselves.
Because the ultimate target, the most dangerous casualty of severe oxidative stress, is inside the nucleus, right? The DNA.
Exactly. A cell's DNA dictates whether the tissue can heal, whether it dies, or whether it turns malignant.
Okay.
In lichen sclerosus, the chronic oxidative stress and the ischemic suffocation we just discussed completely exhaust the resident tissue stem cells.
Stem cell exhaustion. Let's clarify that. Stem cells are basically the microscopic factories that print new skin cells when we need them.
That's a great way to put it. Adult tissues rely on a small, dedicated population of stem cells in the basal layer to continuously divide and replace damaged skin.
But the persistent bombardment of inflammatory cytokines and reactive oxygen species forces these stem cells into a state of premature cellular senescence.
Right. They age at an accelerated rate. Their mitochondria, their power plants deteriorate, and they accumulate massive amounts of oxidative DNA damage.
So they simply stop dividing.
Yeah, the tissue literally loses its innate capacity to regenerate.
The factories are broken. Which completely explains why the skin can't just heal itself even if you manage to calm the inflammation down.
Exactly.
And this cellular exhaustion leads to the absolute most frightening complication of untreated genital LS, the cancer risk.
The clinical guidelines are incredibly vigilant about this grave complication. There is an estimated 4 to 5% lifetime risk of developing squamous cell carcinoma, or SCC, in areas affected by chronic, untreated genital LS.
4 to 5% is a highly significant number when you're talking about cancer. How exactly does the rust, the oxidative stress, drive the tissue all the way to malignancy?
It comes down to the catastrophic DNA damage we just touched on. Oxidative damage doesn't just randomly break DNA.
It doesn't.
No, it directly downregulates vital tumor suppressor genes. Researchers specifically identified genes like P16INK4 and P27KIP1.
Okay.
You can think of these genes as the heavy brakes on the cell cycle. Their entire job is to stop cells from dividing uncontrollably if something is wrong.
So when oxidative stress damages these specific genes, it effectively cuts the brake lines. So the cells, which are already damaged and mutated by the rust, just start multiplying out of control because the safety mechanism is gone.
Right. And the nature of the mutations is very specific. Molecular analysis shows single-base substitution mutations.
Let's break down a single-base substitution for the listener. That's like taking a 3 billion-letter instruction manual on how to build a human cell and swapping out just one single letter.
A tiny typo that changes the entire meaning of the sentence. We see these substitutions specifically at positions like C742T and G818C.
Wow.
But what is fascinating and terrifying is how these typos happen. the data points to the overactivity of ApoBec enzymes.
Wait, ApoBec enzymes, what do those normally do?
In a healthy immune system, ApoBec enzymes are antiviral weapons. They are designed to attack invading viruses by mutating the viral RNA so the virus can't replicate.
Oh, I see.
But in the chaotic, highly inflammatory environment of LS, these enzymes get hijacked and confused.
So they turn their mutating power inward and start introducing errors into the patient's own DNA during cell replication.
Yes, the very mechanisms designed to protect the DNA are forced to shred it. It is a massive driver in the transformation from inflamed tissue to squamous cell carcinoma.
Okay, this brings up a huge point I wanted to cover. We are talking about cancer risk and tumor suppressors.
Yeah.
The research constantly mentions an overexpression of p53 in the skin of LS patients. Now, p53 is arguably the most famous tumor suppressor gene we have.
It is.
If we are seeing too much of it under a microscope, is seeing p53 always a definitive sign that a patient is developing cancer?
This is actually one of the most critical aha moments in recent dermatological research, and it represents a massive paradigm shift.
Oh, really?
Yeah. Historically, seeing heavy p53 staining in a biopsy caused immediate alarm.
Sure.
But the current understanding is that overexpression of p53 in lichen sclerosus might actually be a profound stress-related phenomenon rather than an absolute marker of pre-invasive cancer.
Wow, explain that distinction because that sounds incredibly important for patients.
Think back to the ischemic stress, the suffocation of the tissue. When cells are deprived of oxygen, crushed by scar tissue, and battered by free radicals, they go into an absolute state of panic.
Right.
Wild type, meaning normal, unmutated p53, is aggressively upregulated by these cells as a defense mechanism.
Oh, I get it. The cells are desperately pumping out p53 to stall the cell cycle so they can try to repair the massive oxidative DNA damage before they divide?
Exactly.
Oh, wow. So a patient gets a biopsy, the doctor looks at it under a microscope, sees all this p53 and thinks, this looks like cancer.
Right.
The patient goes through agonizing anxiety, maybe even aggressive surgical treatments, but it might not be cancer at all.
It's the cellular equivalent of a fire alarm going off because the building is filling with smoke, not necessarily because the building is already burned down.
But that is a perfect encapsulation. So heavily staining for p53 might just be the cells screaming for help, trying to survive a hostile, suffocating environment.
Yeah, it highlights just how profoundly the oxidative and ischemic stress alters the fundamental behavior of the cells.
Tricking not just the immune system, but sometimes the clinicians analyzing the biopsies as well.
It's incredibly complex.
This has been an incredibly intense journey into the microenvironment of the skin. Let's pull the lens back and summarize this for you, the listener, so we can see the whole board.
Good idea.
Our core mission today was to find out if oxidative stress drives the severe tissue damage in lichen sclerosus. And the answer is an overwhelming, undeniable yes.
It is the central mechanism of destruction. The rust is what ruins the machine.
It drives the thinning of the skin by destroying the protective fats through lipid peroxidation.
Right.
It drives the dense white scarring by destroying the structural proteins in the dermis. It suffocates the tissue by crushing the blood vessels.
And it drives that terrifying 4 to 5% cancer risk by directly damaging the DNA, hijacking antiviral enzymes, and exhausting the stem cells so the skin completely loses its ability to fight back.
All while wearing a fake mustache to trick the immune system into creating a second wave of inflammation.
It truly is a dark masterclass in how chronic inflammation can fundamentally dismantle a tissue's ability to exist.
Which leaves us with a really provocative final thought for you to ponder as we wrap up. One of the clinical reviews briefly mentioned the systemic effects of psychological stress.
Oh yeah, the cortisol link.
Right. Severe psychological stress elevates cortisol levels in the body, which in turn increases systemic inflammation.
Which is potentially exacerbating this exact oxidative stress loop we've been talking about.
The mind-body connection is undeniable when it comes to chronic inflammatory pathways. Stress quite literally feeds the fire.
So if oxidative stress is the central villain here, if it is the rust destroying the cellular machinery in LS, could the future of treatment completely shift our current paradigms?
Right now, the gold standard for LS is suppressing the immune system with ultra-potent topical steroids. Which makes sense. It stops the rain.
Yeah, but as we've learned today, stopping the rain doesn't magically fix the rust.
Steroids manage the acute inflammation, but they do not inherently regenerate the lost tissue architecture, nor do they replace the exhausted stem cells.
Exactly. So could the future lie in radical, localized antioxidant therapies?
Imagine a treatment designed specifically to manually clear the rust and restore that missing superoxide dismutase cleanup crew.
Or targeted regenerative stem cell treatments aimed at resetting the tissue's fundamental ability to heal itself.
If medicine can figure out how to address the oxidative damage directly, rather than solely suppressing the immune response, we might be able to shift from simply managing a chronic disease to actually reversing the tissue destruction.
It is an incredibly compelling frontier for regenerative medicine.
It really makes you rethink how we approach chronic disease as a whole.
Hmm.
It's not just about stopping the storm. You have to figure out how to rebuild the foundation underneath.
Well said.
Thank you for joining us on this deep dive. Keep asking questions, keep looking past the surface, and always stay curious.